Let's have a go at this together. When we're solving algebraically, we just remember those three conditions that we talked about here. So we want to solve these absolute value equations. Now the first one, we've got 3x plus 6 is equal to negative 21. Now here, I'm just going to write here, 3x plus 6 is equal to negative 21. Now if you remember my three conditions, and my three lines I drew, is the value of k negative here? Yep, it is. Minus 21 is negative, and so because of the shape of my graph, it's never going to actually touch my absolute value function here. So here, because the value that we're solving for is negative, we're not going to get a solution. We're going to get no solutions here. Solutions, because, well, and I'm going to write, because negative 21 is less than 0. Because that's less than 0, those two lines are not going to touch. So we're not going to get a solution for this first one. Okay, that one's nice and easy. Knock that one out. Next one, absolute value of 3x. I forgot the absolute values there. Whoops. Absolute value of 3x plus 6 is equal to 0. Now when it's equal to 0, if you have a look at the conditions that we had up here, all we're doing is we're finding one solution. There's going to be one solution to this equation. And that's where ax plus b is equal to 0. So here, let's just solve it. So absolute value of 3x plus 6 is equal to 0 just gives me 3x plus 6 is equal to 0. So when I solve that, I move that minus 6 over to the other side. I've got 3x is equal to minus 6. And I divide both sides by 3. X is equal to negative 2 for this one. So here we've got one solution. X is equal to minus 2. Now the final one is absolute value of 3x plus 6 is equal to 21. Now you remember back up in my shape. If k is greater than 0, we're going to have two solutions, and we have to look at both branches of my absolute value function and solve for each one of them separately. So what I'm going to do here is I'm going to go, well, first case is I'm going to go 3x plus 6 is equal to 21. That's the positive branch, so that light blue side that I drew. So here I'm going to just solve it. I've got 3x is equal to 15 and x is equal to 5. So that's my first solution. But because 21 is positive, we're going to have a second solution, which is when 3x plus 6 is equal to not just 21, but minus 21. Minus 21. So here I'm going to get 3x is equal to minus 27. And so x is equal to minus 9. So here I'm going to write at the end, therefore x is equal to 5, or x is equal to minus 9. That's my final solution for this question here. So hopefully from this question you can see what happens when we've got different values of k. If k is a negative number that we're solving for, then we have no solutions, which is what we got on this first example over here. Because that absolute value functions cannot be negative. For the second example, because it's equal to 0, we're going to get one solution, like this example over here. Because when it's equal to 0, it's just touching it at the vertex of your absolute value function. And the final example is if it's a positive number, and this is the most common case that you're going to deal with, you're going to have to look at the positive case. So when 3x plus 6 is equal to 21, and also the negative case when 3x plus 6 is minus 21, and I'm going to put a circle around that, because you've got two separate branches that you're solving for, two separate linear functions that make up your absolute value function that you have to solve for. So here you're going to get not one solution, but actually two solutions. So this is the first example of solving absolute value functions algebraically by doing this method. I'm going to go through a few more examples. There's two more that I want to go through, and we're going to solve these algebraically again. So we've got x minus 2 is equal to 3. 3, let's have a look at this first one. Absolute value of x minus 2 is equal to 3. So we're going to have to look at two cases. The first case, what's the first case? Well, the first case is when x minus 2 is equal to positive 3. And so here, I move that minus 2 to the other side, so we've got x is equal to 5. Because 3 is positive, we have to look at the second case, which is when x minus 2 is equal to negative 3. So here, x is going to equal to minus 1. So for this example here, therefore, x is equal to 5, or x is equal to minus 1. Okay, whoa. Okay, hopefully we're starting to get the gist of it. Okay, question B. I've got 7 minus 1 over 4x. Absolute value of that is equal to 3. And so 3 is a positive number, so I'm going to have to consider those two cases. Firstly, when 7 minus 1 over 4x is equal to 3, and so I'm going to move that 7 to the other side, so negative 1 over 4x is equal to minus 4, and so x is equal to 16. And the second case is when, well, we've got 7 minus 1 over 4x, so the stuff inside my absolute value is equal to minus 3. And so here for this example, I've got negative 1 over 4x is equal to minus 10, so x is equal to 40. And so here, my final answer is x is equal to 16 or x is equal to 40. I'm going to put it therefore at the front. Okay. Hopefully by now you're starting to see how we do this. When we're solving absolute value functions, we have to often we get these cases where the number that we're solving for is greater than 0. So we need to consider the case where we have to consider both cases of those both branches of your absolute value function. Okay, so that's solving algebraically.